Hello everyone, thank you for joining us for our today's expert webinar titled Streaming Real-Time Data with Kafka. I'm Siddharth from Spring People and I'll be the session moderator for today. Spring People is India's largest enterprise training provider. Our speaker for today's session, Mr. Pradeep, comes with more than 18 years of extensive experience in building fault-tolerant, highly scalable, cloud-native applications. He has expertise in writing clean code, domain design principles, and he conducts workshops on building production-tolerant, great web applications, covering all the challenging concerns. Kafka is a distributed system that can be used for event streams in near real time and near real time. In this webinar, we will discuss some key highlights of real time data streaming and use cases. Over to you, Mr. Pradeep.
Okay, thanks, Siddharth. Good afternoon, everyone. My name is Pradeep, and I will be working with you for the next 1 hour to understand data streaming with Kafka. All right, so we will begin our discussion by understanding what is Kafka, so what are the different modules of Kafka. So we will be looking at what are Kafka streams. Then we will be looking at few use cases of working with Kafka streams, followed by a demo session where I will be walking you through the internal implementation or how do you use Kafka to build a real-time data streaming, where you are going to stream some data and then we'll be processing them in real time. So let us begin with understanding of what is Kafka, right? As you look from the screen, Kafka means different from different perspective, right? So there is a saying, right, that there were 6 blind men, and the king asked them to describe what is the definition, right? How do you describe an elephant? So the person who touched his trunk told that it looks like a snake, right? The person who touched his tail told that it resembles a rope. The blind man who touched the body told that it looks like a wall, and the one who touched his ears told that it is a fan. And the final person who touched his leg told that it is a trunk of a tree, right? So is it correct or is it false, right? So it means different from different perspective. Although all of their definition are true, but it is a totally different beast by itself, right? So what is Kafka? Kafka is a streaming distributed system which can be used for variety of use cases, right? So in the context of today, where we are moving towards a data driven, where we are moving towards event driven, right, where we have large amount of data to process, so Kafka is much relevant as of today than ever before. So what are the real use cases that we can use Kafka for? So Kafka can be used for data streaming, right? So what are the use case of Kafka? So Kafka can be used for data streaming, where you can stream millions of records in a few seconds, right? Millions of messages per second. So Kafka can also be used for tracking user activity, right? So website click events, right? What the users are searching on your website. So these are all the things that you can easily track and make more informed decisions on how to get the insights from your data. Kafka can also be used for aggregating your logs, where you can use it as a commit log, where you can store all the logs in an append only manner. All the logs will be stored in a commit log on a disk, right? It is durable. More often, the Kafka can also be used to decouple systems, right? So we can decouple both producers and the consumers. So these are the different use cases, and it can also be used for replacing your ETL types of jobs where you do mostly the batch processing. So you can actually get the meaning of the data in real time, right, or in near real time. So how is Kafka different, right? So this is how your architecture looks like without having Kafka. So basically, where you have multiple producers and multiple consumers, right? They are talking to each other, and it leads to a spaghetti code, correct? So where you have producers who are talking to each other, and this actually leads to a lot of issues in terms of maintaining the code, refactoring the code, testing your code. and they are not truly decoupled, right? Anytime we add a new endpoint or we add a new destination, so a lot of the changes has to be done in all the source in order to make sure that they are running, right? So in order to totally decouple the systems, the producers and the consumers or different microservices, we can introduce this additional hardware or additional infrastructure, which is going to decouple both the producers and the consumers. Now, the producers are going to be pushing the data to the broker. So we can also call this as a broker. And the consumers, on the other hand, will be consuming the data, right? So the producers can be anything. It can be a .NET application, it can be a Java application, it can be a Python application, it can be a database, right? It can be an IoT device, or it can be any other who will be able to produce some data and then which is of business value, which can be durable onto Kafka. The messages are durable on Kafka. And on the consumer end, so the consumer is going to pull the messages from the broker, and the consumer is going to process those messages, right? So this is the overall architecture of Kafka, right, in very high level words. So what is the definition, right? So Kafka can scroll to hundreds of nodes. It's a truly distributed application where you can add additional nodes, additional servers, and ensure that you can scale your Kafka to hundreds of nodes, right? So each of the node is also called as a broker. Kafka is horizontally scalable. That means what you can add more number of worker or nodes into the cluster to ensure that you can scale to any level, right? So Kafka can also, with even with a single broker or a single node, Kafka can handle millions of messages per second. It can also be used for real-time data processing, right? Let's say there is a sensor which are attached to a automobile, and the automobile is traveling, right? Automobile, we are moving by the automobile. The automobile can emit notifications, right, with respect to the speed, right? Any changes in the variation in any of the sensors, right? And this can be tracked in real time. This can also be used for tracking stock related things and give recommendation. It can also be used in healthcare industry, where we can actually track the different state vitals of a patient, and then we'll be able to take some informed decisions, right? So the use cases of Kafka, the use cases of data streaming in general is of very high importance, right? So we'll be able to easily track and monitor or make the sense of the data. So in the context of microservices, where most of the applications in today's world are breaking from monolithic application into microservices. So in these cases where we cannot establish the transaction boundaries via the traditional transaction boundaries, asset properties, so we can use event sourcing, where you are going to use event sourcing to source all the events, right? So events are going to be the source of truth, and we will be able to process those events in an eventual consistency manner. So these are all the variety of use cases that you can use Kafka in product in today's context. Okay, so let us look at the what are the core traits of Kafka, right? So at the heart of Kafka, so we have the concept of topic. So what is a topic? A topic is just a logical name to send messages, right? So let's say you are sending in courier to, let's say, New Delhi, right? So New Delhi becomes, let's say, for example, a topic. Now, it is just a logical name, right? So you are going to ship the courier to a specific person, to a specific address, to a specific pin code, right? So topic is just a logical name, and the topics can span across the different nodes. Internally on the disk, right, at the disk level, the topics are broken down into something called as a partitions. So topics are broken down into something called partition or split into partitions, and multiple partitions together form a logical unit called a topic. So the producers and the consumers are going to interact with the topic. Internally, they are speaking to a partition. So the messages are written on the disk in a partition block. So the partition enables a topic to be distributed across the cluster. So that means we can have multiple partitions across the different cluster, and they make up the topic. Topic are also the point at which you can scale horizontally from the producer end. Topic you can think of partitions, you can think of them as unit of parallelism. So if city name is the topic, you can think of the pin codes as your partitions, right? So every email, every mail that you are going to send to a particular topic will have to be routed to a specific partition, and then the more number of partitions you have, the more number of parallel unit of work. So it also refers to as a unit of parallelism. So it is just a logical name. The topic happens to be just a logical name, but partitions are the one which are there as a files on a individual broker. So essentially, you are writing the message, right? The messages are written to a the partition file, the file, right, which is residing on the, and topics can span across nodes with partition. So what is the meaning is that let's say you have a different brokers. We are running in a clustered environment. So these are the three nodes or three brokers. Now this topic A has been divided into three partitions: partition 0, partition 1, and partition 2. So you can think of them as the files, right? You are going to write. So Kafka is basically an append only. So you're going to write it to the end of the file. So partition happens to be the files on which you are going to write the content, and you are going to obviously put the partitions distributed among the different brokers. So you are going to distribute the partitions among the different brokers, and in this case, the topic B has two partitions. So basically, you are going to distribute them across the broker. So obviously, you are not going to put um, partitions on a single broker, because if the broker dies down, if the broker goes down, if there is a internet disconnect, right, network latency, or the hardware crashes or the OS crashes, right? So we don't want the messages to be lost on the partition. So it is always a good practice to distribute the partitions among the available number of brokers, right? So when we create a topic, we are going to upfrontly decide the number of partitions that the topic is going to, and based on the number of guidelines, so we are going to create the number of partitions for a given number of topic. So partition can also be considered as a log, right? So what is this partition? Partitions are basically where you are going to store messages, and messages are stored in a partition using an offset. So if this is a topic and if this is a partition, the messages are going to be stored in any one of the partitions. So if a message producer is sending a message, the message can be on either one of the partition, not all, either of one of the partition, and the messages are always appended to the end of the partition log, right? So offset are assigned to a message, and offsets are unique to a partition, right? What does that mean? That means every message is going to get an offset, and the offset is unique within the partition. Let's say the offset is 4. The message within this particular partition is going to have a 4 offset, whereas on this partition, the message, a different message will have an offset 4, whereas in this partition, the different message. So offsets are unique for a specific partition in a topic. Or also, messages are always ordered only within a partition. It is similar to the example that we were discussing, right? Let's say you have a, let's say everybody sends a mail to a specific pin code, then the messages, the mails are always in order. So if you want order, then you have to ensure that you are reading the messages also from the same partition. Obviously, the messages are going to be put on a partition, and the messages are always appended to the end of the partition. So always the messages within the partition are going to be ordered. So one topic can contain more than one partition. Topic is just a logical unit. Partitions are the files on which you are going to store that, right? So that is the different, that is the relationship between topic and the partition. So how are we going to decide on which partition we are going to display, right? So if I'm going to ship a courier to, let's say, a place in New Delhi, so I'll have to tell, right? So on which pin code I need to send the messages. So the pin code is considered as the key on to which you are going to send messages, right? So every message, if you are going to assign a key, always it is going to compute the hash. It's going to compute the hash, and it is going to always go to the same partition, right? Just like in your hash map, if two objects have the same hash key, obviously they are going to go into the same bucket. Same with the case of partitions. Whenever any message, two messages are having the same partition key, they are going to be on the same partition. So if you want to have messages which are processed in a specific order, right? Let's say for a customer, you are processing an order, and then you are processing the payment and processing the shipment, and you want the messages to be in order. You want to make it accept the payment only after the product has been accepted or the order has been accepted, and you also want to do the shipment only after the payment is done. So it ensures that the messages are to be in order, and when you want to place the messages in order, you are going to ensure that they are going to the same partition. And how do you make sure that they are going to the same partition? You're going to ensure that by placing the message key, right? So if you do not give the message key, then the messages are going to be allocated to all the partitions in a round robin algorithm. So basically there is no specific message key. When the order does not matter for you to process, in those cases you are going to ensure that the message, even though if you don't give a key, they will be assigned to any of the partition, right? Messages are ordered only in a partition. Partition key dictates the partition, and if you do not give the key, then the message will be assigned to a random partition. Now there is a dependency on the zookeeper, although as a producer or a consumer. So either you can be a producer or you can be a consumer. So if you are either producer or a consumer, you are going to interact only with the broker. And but to run efficiently the use cases of broker, so to ensure that the broker is running fine, even if there is an addition of broker or if the broker goes down, so to ensure that there is a the brokers are healthy, they are able to recover from the failure, right? And they are going to get notified about the broker going down. So to manage the brokers, so we have the concept of zookeeper to manage the broker. If the broker goes down, then somebody else has to take the responsibility of the broker which went down, right? So in those cases, or a new broker has come up, then we also have to repartition or apply the partitions to all the broker, right? So for those reasons, so you need a zookeeper, and you can think of zookeeper as a ghost module or the ghost system which is working behind the scenes to manage the list of brokers. So you are not going to interact with the zookeeper directly. You are going to only work with producers and consumers and the Kafka broker. But to maintain the list of brokers, so you need a zookeeper. The zookeeper works behind the scenes. You don't have to handle or need to work with zookeeper. Although the Kafka team, right, is reducing the dependency on the zookeeper to an extent that at some point in future, you your the load the responsibility of the zookeeper will be shared by the brokers themselves, right? So that is the scope of the zookeeper, beyond which you don't have to invest any time in understanding what is the scope of zookeeper in the context of Kafka. So Zookeeper also can go down, right? So it is a distributed system. In case of distributed system, things are not always happy, right? So you can any system can go down. There can be network latency, right? Any system can crash, right? Hard disk can crash, OS can crash. So for that reason, Zookeeper also works in a clustered mode. All right. So this is the complete architecture that we see as of now. So we have producers who are producing the messages to the broker, consumers who are consuming the messages from the broker, and all the metadata of the brokers, right, which is running in the context of a Kafka cluster, is managed by your Zookeeper. So Zookeeper manages the metadata of the broker, producers push the messages, and consumers consume the messages from the broker. All right. So I see a lot of these questions, so I'll be taking up these questions towards the end of the webinar. All right. Okay, so with this is the core of your Kafka, right? As you work with the higher order modules of Kafka, so you need to know at least the basics of what is a producer, what is a broker, what is a partition, right? And then it gives you sets the stage for you to work with the Kafka streams. So what is a broker? So broker is a single node managed by the zookeeper. Set of brokers forms a cluster, right? So you have more than one broker, and then you are going to form a cluster. So topics are created are distributed across the brokers, and in case the broker goes down, the zookeeper rebalances. Means the zookeeper will manage the brokers. If the broker goes down, it will do the rebalancing. If a new broker is added, it will again do the rebalancing, right? So that is the state of what the broker does. So this is how your entire architecture. So for whatever we have seen, so this is how it works. So we have a cluster, we have a topic. Topic is just a logical name. I'm emphasizing again. Let's say this topic is made out of four partitions: partition 0, partition 1, partition 2, partition 3. Now the messages will be scattered across all of these partitions, and the consumers will be consuming, right? So this is the flow. Now let's add a twist into this tale, right? What if this broker goes down, right? What if the broker goes down? So anything can happen, right? The broker can go down. How do you add redundancy into this particular model, right? The messages are lost. How do you ensure that the messages are not lost, right? So after all, Kafka is a durable system. So when I say durable, so it is fault tolerant as well. Fault tolerant in the sense it is able to recover from the errors or the failures. So to ensure that there is a redundancy, to ensure that it is fault tolerant, so messages are replicated. Replicated in the sense, so you are going to keep a backup of all the partitions across all the other partition, all the other brokers. What do I mean by that? That means if the partition 0 is on broker 1, so I am going to have a copy of this. So this is called as the leader partition, and we are also going to have a replica or a copy of this partition on another broker, right? And it is the responsibility of the follower to ensure that they sync the changes from the leader partition. So these things happens behind the scenes, that the leader partition and the replication. The replication partition is on another broker, and its responsibility is to sync the changes whichever is there from the leader partition. So from the perspective of both the producer and the consumer, they only talk to the leader partition, right? They don't talk to the followers. All the interaction with the broker via the producer and the consumers always happen with the leader partition. And the follower partitions are just there to sync the changes, to add redundancy, right? So what does that mean? The replication is nothing but it's a making a copy of the partition available in another broker. If the broker goes down, then the messages are there in another follower partition. So this is how the Kafka is fault tolerant, right? To broker and partition failure. If the broker goes down, then another broker will be elected as the leader broker. That is, the follower will be promoted as a leader. Both the producers and consumers are always served from the same broker, right? That means from the leader broker, you are going to serve the request. So in case of broker failure, the partition from another broker is elected as a leader. The follower is promoted as a leader, and then it then takes over the responsibility of working with the producers and consumers. Obviously, you're going to ensure that the follower is always in sync with the leader. So as in the case of any broker failure or the leader partition fails, so you need to ensure that the follower who is being elected as a leader is in sync with the leader partition, or is able to completely be up to date with the messages that were there in with the leader partition, preventing any message loss. Okay, this is the state of thing that you need to be aware before we even get into Kafka Streams. So this is the core framework. This is the core underlying architecture of Kafka. So these are the topics that you need to be familiar before moving on to the Kafka Streams. So what do you mean by Kafka Streams, right? So from the producer perspective, it can be an IoT device. It can be anything which can connect to the internet, right? So the producers are going to emit notifications, right? Whether it is a web click event that is happening on the website, whether it is a patient's data that is actually getting uploaded, right? Whether it is an automobile sensors that are emitting events. So what we want is we want to ensure that these data are utmost relevant, right? What do I mean by this? So the cost of the data, the meaningful, the usefulness of the data depends on the time at which it is consumed. What do I mean by that? That means, let's say there is a series of actions that is happening. Let's say there is a stock price, and there is a surge in the demand, and the price of the stock price goes shoots up within a span of 2 minutes. So if you are able to process the data in real time, right, within fraction of seconds, you will be able to make informed decisions, right? You will be that there is a meaning for that particular data, and the messages are in the raw form. They are just a data, and the moment you add some business value, you when you make it as an event, you are processing not as a message as in the batch processing. You are processing them in real time to react to an event, right? So event is nothing but it is a message, but it is happens in the past tense, right? It is immutable, and it is of some business use case, business significance, right? A particular stock was able to shoot out from this particular range to 3 times within a span of 2 hours. So it is a very important event, and then processing that in real time will help application business to solve very important use case, right? Let's say there is a series of fraudulent transactions that are happening, right? So instead of waiting for the end of the day and assuming that the transactions were fraudulent, so in case you are able to see that a particular credit card has been declined 3 or 4 times, then you can take some action immediately. Let's say a driver is driving recklessly, and he is applying the brakes continuously. Within a span of 15 minutes, he has applied already 7 times or 8 times. Then those events are of utmost usefulness, so that you can process those events, and probably call the driver, right, to ensure that it improves the passenger safety. So the use cases are enormous, right? So you can move away from your traditional batch processing to processing these events in real time. So this is where Kafka Streams comes into picture. Because Kafka Streams is a high-level DSL, domain-specific language, which is built on top of Kafka. So it is a separate module that comes to ensure that you will be able to write stream processing tasks out of the box. Most of the tasks, right, predicates, functions, map, right, consumer, all of this lambda expression, all of these functional interfaces that we are familiar with Java can be easily translated into the Kafka streams. Kafka streams by default comes up with lot of these tasks which you can use compose to build a higher order function. So it allows us to build a fluent interface, right? Just like we write SQL syntaxes, right? Select star from this customer where salary is greater than this, order by their first name, and limit only to 10. So you will be able to write fluent interface style of programming, and you will also be, the emphasis here is on functional style programming. So you're going to write functional style programming and use these functions to build a higher order function. So this is more of convenience, right? Or you would tell that it is out of the box, it supports. It gives you much more convenience. It is declarative style of writing code. But let's say you want to do more. You want to handle your exceptions, right? You want to have a specific use case that you are not able to solve using your functional style. Then there is a lower order API called processor API, which can be used for having more control. So they give you the APIs for writing your consumer logic directly. So you would ask me a question. So we have a producer API, we have a consumer API in Kafka natively. Why should we go for streams, right? So working with streams will avoid all the complications or complex things that you need to do when you're working with consumer API, right? So Kafka Streams is an out-of-the-box solution that you can use by using their functions to ensure that you can write complex use cases within very few lines of code, right? We are going to look at these use cases. So what do you do in Kafka Streams? So at the outset, so we build something called as a topology. So this topology is nothing but it is going to have a source which is an emitter, and you are going to have a destination. So you have a source and you have a destination, and you have different transformers in the middle. So whose job is to convert, apply the transformation, whether it is a filter, map, a reduce, function, predicate, right? Any of these transformation, and it is going to push the outcome message into a destination. So your job is to ensure that you read from a specific topic, process them, and then emit into a different. These are called downstream topics, right? So this is how you are going to build a topology. Now it is not always one direction. So you can, it is always one direction, it is unidirection, but you can also ensure that you can build a completely comprehensive topology using Kafka Streams. So this is one more use case that we are going to look at. So we are going to look at this use case where you're going to have a source code, a source. We are going to get the source, and we are going to mask the data. Let's say we are getting a data of transactions, and every transaction will contain the credit card number through which the transaction happened. And before we further do any other processing, we have to ensure that the the credit cards numbers are masked. So from the source, we are going to mask the credit cards and push it onto a separate topic. And from this topic, so we can actually generate different use cases. So there is one use case where we want to consume all the messages, but we want to filter out based on the transaction value, right? So let's say there is a sale, but you are not interested in the sales which are less than $100, right, or 1,000 rupees. So we are going to ensure that the sales are give me all the transactions which are more than 1,000 rupees, right? And those things can be put into a separate topic, and from there it can be served by different downstreams. So we can also take the transactions and apply a rewards, right? For example, for every purchase that you are doing, we can ensure that you are going to get a 10% off, or 10% discount, or 10% 10 points. So basically you can accumulate the points and give some bonus, right? Give some, or you can apply some transformation to get their customer email address and use it for ads, right, or ad tracking. So you can, or you can also use this for transactions to ensure that you are able to do audit, right? Or you can also use this transaction data to actually do customer service, right? So the point here is the data is available onto you, with you in the topic, and in the form of events. And then any customer, any consumer, right, they can be able to replay those events, right? So it is like an event log that has occurred, and any application can then replay those events and infer the business use case. So we are going to do one thing. We are going to use this topology. We are going to see this in action. So the first topology that we are going to look at is we are going to look at the transactions. We are going to mask the credit cards from the source stream. From the source, from this particular thing, this is now going to act like a source stream. And from this stream, we are going to extract the information from the transaction. We are going to extract based on the zip code to determine the purchase pattern. And we are also going to identify the customer and find the amount spent. So basically, we should be able to do this, right? So how can you replay an event? So in case of so that is an interesting question. So how can we replay an event? So it turns out that the messages in Kafka are appended to the commit log, right? So what does that mean? That means the messages are stored in a Kafka broker as an event. So in this case, events are the source of truth. So what is a use case? This is a pretty good use case. Now let's say a customer walked in, he added item 1, he added item 2 to his cart, and he added item 3 to his cart, and finally he decided to remove item 2 from his cart, and then finally went with the checkout. So if it was a traditional DBMS, you would actually store this as your line items for a specific order. So order to line items would be one to many. But in a database, this information would not be present because this items was never part of your. Now this is called data as source of truth, right? This specific thing is called data source of truth. Now consider this using events as source of truth. So if you treat them as events, the customer logged in will become an event. Customer added this item 1 will be another event. And event are going to be in past tense. So events are always in past tense. So events are immutable and events are read only. Item 1 was added, item 2 was added, item 3 was also added, and item 2 was removed, and this is also marked as an event. Now the data is appended to a file, so it is appended to the durable system. Now all your applications can replay those events from the beginning and will be able to infer the data, much more like your passbook, right? We have State Bank of India, State Bank of Mysore, this passbook. What do we do? Every transaction is recorded and we can arrive or derive the data based on the event. So if you replay all these events, you'll be able to derive the, so the data becomes the byproduct. So in the event source, the data becomes the byproduct. And if there is a, let's say there is a bug in the code, and if it tries to access this, only the code gets corrupted, so the data is not corrupted. Whereas in case of database, what happens is if your code is there is a bug in the code and it upsets the table, the records is gone because there is no versioning in case of database, right? You can do that using triggers and other things, but at the end of the day, the whole point of database is just for snapshots, right? So in this case, you are going to ensure that even if there is a bug, the application can fix the bug and replay those events to generate the data, right? And the good thing is all your, there can be multiple applications and your database can also be a consumer. So every time you append a record into the Kafka, so this will be translated into a record, or the database can also be a producer. In this case, whenever you're going to insert a record, that can be pushed into Kafka. So you can actually use it like a hub and spoke model, right? Hub and spoke model. Now we are going to look at this topology. How are we going to do that? So let me quickly show you the code. All right, so this is our Spring Boot application. I'm going to show you the code. So we are having a producer who is going to produce the messages, all right? So we are generating a mock data producer who is going to generate a lot of these messages, and then he's going to push the messages into the topic. And we are going to have this particular code where we are going to write our topology, right? So we'll look at the topology. First, we are creating a instance of stream builder. This is our steps. We are going to build a stream config. And we are going to build the serverless. Serverless stand for serialization and deserialization. We are going to ensure that we are going to take from the transaction, which is the source topic, and then we are going to map that to a function for masking the credit card. So what we are doing is we are applying a map. And what is the function of a map? Map is basically a function which accepts an input and returns another output. So in this case, the messages in the incoming messages happens to be a product message, and the output is also going to be a product purchase, but the purchase object, but with the masked credit card. So basically, what we have done is we have taken the system into the taken the message into the system, and you are going to mask the credit cards and send it back. And this is going to be the source which I have masked. I'm going to print that to a console. And what I'm going to do that is from this particular masked thing. So we are going to create a rewards. So to create reward points, we are actually creating a message. From that, based on the zip code, we are taking and creating a separate purchase pack. So this is one of the things that we are doing here. What we are also doing is we are taking the same purchase case stream and we are applying the reward accumulator. So what we are doing is we are taking the purchase object, get the first name and I get last name, get the total value, and apply the reward points. What I'm doing is I'm taking the price and applying the quantity and multiplying that, and then give them a total reward points. So that is what we are doing here. So apply after we apply here, we are also going to filter. We are going to filter from the purchase history, and we are going to remove the thing which is less than five rupees, right? And what we are doing is we are putting that. So finally, you are pushing that into the purchase stream. So by the end of this, you should be able to see that here. And what I'm also doing is if the purchase is of type coffee, then I'm going to push that into a separate. So what I'm trying to tell is based on the type of purchase, if it is the item that was purchased is a coffee, I'm going to put it in another branch, another topic. And if it is electronics, it is going to put it in some other topic that we are going to use by using the branch. So all these operators, just like if you are familiar with streams API in Java or lambda expressions, so this should be somewhat very correlatable, right? And what I'm going to do is I'm going to take the streams and I'm going to start. So if you look at this, there is not even a single if block, switch block, for loop. It is very, very declarative in nature. So you're writing the code as if you're reading, right? Like in English like sentences. And this is the whole point in building the streams API. So you're actually building the topology, and the topology itself will not execute unless you call the start. So that is one of the beautiful thing. So you are going to create streams, and if this is a microservice, you are going to create any number of instances of this, and they're all going to share from the same topic. So from the same topic, we are going to share based on the number of partitions. The partitions will be equally distributed among all these stream tasks, and they will be able to process them in real time. So with that being said, so there are other things we can go through that, but we are going to run through this application and we are going to see this in action. So this is a Spring Boot application, and I have already created, I'll be connecting to this. So this is my Kafka cluster. I'm going to create I'm also going to create one more window here. All right. So what I'm going to do is I'm going to first check for the push the messages, and I'm going to start this URL. So let me run through this. So now what happens is the generator is going to generate some messages, and he's going to push the message into the producer, right? Transaction topic. So the messages started pouring in, and what we can see here is I'm going to show you the sh Kafka topics in a list. And we can see here there are the topics that got created, right? So we have your transaction topic, source transaction. Then we have rewards, purchases, patterns, coffee. So let's do one thing. Let's subscribe to these things, right? So sh Kafka console. So consumer, and I'm going to write topic name. Let's say, for example, the rewards. Bootstrap, localhost. The same thing I'm going to do here, but here I'm going to go to topic name, and here I'm going to go to some other things. Right, we should be able to see some messages coming here, and we should also be able to see some messages here. You can see that the messages are coming here. Let's do one thing. Let's run this. And you should be able to see the messages coming in, all of these things. And these are of business value, right? You can process them in real time, right? So this is only going to contain the topic messages to order for coffee. This is for the one which is the reward points. So you can see here that purchase date, and we are going to get only based on this. And here also we are going to get the purchase total reward points based on the number of topics, the items that you purchase and the quantity. So this is how we will be able to do that. We can actually add more things into it. We can add state, and we can also count or partition them based on the time frame, right? Let's say, for example, in the last 24 hours, find out the highest temperature for this patient during the span of half an hour, right? So you should be able to get the highest temperature for every half an hour for the last one day, right? These are the things that you can apply in real time with very few lines of code in a very declarative manner, and that is the powerful feature of Kafka. So this with this we have done with the lab. Now you can also apply stateful processing. This is the example that we did was with respect to the statelessness, right, where we are only emitting an event. But with the event, if you are able to add some meaning context, then you are going to get a whole different input, right, insight into the application. Let's say there was a credit card declined at 9:51 a.m., 9:53 a.m., 9:56 a.m. So each of these can be treated as a transaction decline. But if you add some meaning with respect to the time, you can see that within a span of 2 minutes, that credit cards were declined. So the idea here is there is some use case of fraudulent activity, right? So these are the things that you can build when you add some state to a particular event. Event plus state will give you more context thing. So you can add the state by using a store. Basically, you can have any in-memory data store where you can store, and then you can process with the statefulness, right? So the idea of state is basically data locality from performance consideration, faster lookups, reduced latency. If you're having the data store within the scope, within the cluster itself, so there is faster lookup, reduced latency, and no data is shared with different threads. So it improves this one, concurrency. And you can also store those data within the database, the data store. Internally, it is a DB called RocksDB, and the data itself can be backed up into a separate topic. So these are the things that you can do much more in terms of Kafka streaming when you add a state also. So these are the use cases that are very, very useful, especially in the context of microservices, especially in the context of event sourcing, where you're going to source those events, where events are considered the source of truth. You're going to implement transactions using Saga pattern, both using choreography or using orchestrated. And in transactions using microservices, it is going to be not a strong consistency, but in case of weak or eventual consistency. So in case of microservices where different microservices are running in different VMs, JVMs, you cannot apply transactional boundaries to all these microservices. So transactions diminishes in the context of, there is no transaction boundary, or the scopes of transaction boundary diminishes in the context of microservices. And in those cases, you are going to use eventual consistency, and you are going to favor towards a choreography or orchestrator based Saga to implement transactions. So this is just a bit of what we wanted to cover to bring the awareness of where we are headed towards, right? So we are in the context of where we have huge amount of data, and how do you process the data in real time, and what are the use cases of Kafka with respect to the different use cases like microservices, data streaming, right, analytics, right? And this picture holds very good true to its meaning. And we, from our Spring perspective, Spring people, so we also offer different training programs with respect to Apache Kafka fundamentals, Kafka streams, right, and data-driven architecture using Kafka, so which are certification related. courses. So with it being said, I am opening it for
Uh,
the question.
so yeah, thank you, Pradeep. Thank you for your valuable insights on Kafka Streams. I'm sure it was a very informative session for all the participants. If you guys are interested in learning more about various Kafka trainings, then do check out our super discounted batches on virtual instructor-led trainings. And you can check them out at our website. It's called springpeople.com. These VILT trainings can be leveraged online from the comfort of your home, and they're flexible as per your schedule and location. The links for these courses can also be found in the chat box. If you do not find any suitable batches, we'd be happy to schedule a private batch for you. For further info, do write to us at training@springpeople.com, or you can even call on the number displayed in the current slide. So now we'll open the forum for Pradeep to answer the questions. Since we have time constraint, we'll try to answer as many questions as we can. So without further ado, Pradeep, you can take over. Thank you.
Right, thanks, Siddharth. So there are a lot of questions. So I'm really, yeah. So look very good in terms of engagement. So we'd like to take few questions for answering. So the question is, what is eventual consistency? So eventual consistency, in the sense, your system is going to go to a consistent state eventually, right? So in case of transaction, what happens? What is transaction? So you are going to apply either the transaction should happen or it should roll back, right? But in terms of, let's say you are applying or you are ordering something on, let's say, Swiggy, right? Your money is already deducted, right? And you have already been raised invoice, but let's say the shipment did not come, the delivery boy did not come, right? In those cases, you are going to cancel the order. So how are you going to undo the transaction? Like the money is already deducted. So you're going to reinitiate a new transaction. That is called a refund. So you're not going to undo the transaction. You are going to apply a new transaction. So this is called eventual consistency, where you're going to go from one consistent state to another consistent eventually, right? So what is the difference between choreography and orchestration based saga? So basically, when microservices are communicating with each other, so where do you add the logic, right? So either you can add the logic in each of the microservices where they are going to emit the events to a specific microservice, or we can write a dedicated facade where we are going to write all the rules, right? So if you are writing the facade, so then it is referred to as a choreography orchestrated based saga. And if the microservices themselves are able to communicate, coordinate, it is called as a choreography based saga, right? So I will be yeah, Spring people will be sharing the report link, report details. How do you how to use power of Kafka streams in Python? Kafka streams is basically VM, so it is basically built on top of you can use Java, Groovy, Scala. But to work with Python, I think you need to use some adapters or something. I'm not sure how natively it is supported with Python. So how does the follower know if the leader has failed? What is the synchronization strategy? So basically, there is something of the concept. There is some concept called as ISR, in sync replica. So the broker is going to always look at the in sync replicas, and if the broker fails, the zookeeper will identify that the broker has failed, and it is having the list of the leader follower partitions who are in sync with the leader partition. So the zookeeper will consider the first who is in sync with the leader partition and promote the follower partition to be the leader partition, right? Yeah, I read somewhere that the new Kafka version doesn't need a Kafka Zookeeper. Yeah, Zookeeper, I said you're right, the dependency with Zookeeper is reducing with every future version of Kafka. But as of today, in production, still they recommend using the Zookeeper. Is Kafka like a middleware application to connect to each nodes? Yeah, Kafka is, you can think of them as a middleware. We are going to add a new infrastructure where the producers and consumers are going to. The producer can be your application, the producer can be a database, the producer can be, let's say you can have a MySQL database as producer, and let's say Neo4j as your consumer, right? Both of them can be connected, in which case you are basically converting from one data set, one form of data to another form of data. How to monitor Kafka? There are some other tools which will help us to monitor Kafka, right? What is the max size of messages can be handled? By default, the maximum size that is recommended by Kafka is 1 MB. beyond which, if you add the increase the size of the messages, the throughput is going to reduce, the latency is going to increase, right? The disk space, the disk utilization will not be optimized. So Kafka recommends that you need to have the messages size which is less than 1 MB. So if you're going to send a file like a blob or a video object, then it is recommended to store the media on an NFS server or a S3 if you're using AWS, and then you can use that link in your message payload. Okay, so how long the events live? The messages are by default live on the broker for 7 days, right? So you can decide how long, how durable the messages are. The messages can be made durable for months, weeks, years together, or you can also decide that the messages should be deleted once it meets some size threshold, like 2 TB, 2 GB, 20 GB. You can tell in both size as well as time constraints. So Kafka is an open source project. So the company which backs this Kafka is called Confluent. Confluent comes up with many add-ons. Confluent also comes up with a paid version, right? Subscription based services. All right. So I would like to take one more question. That is, we do have other technologies like Elasticsearch Stack, Splunk, which stores data based on events. What are the advantages of Kafka for this? Kafka is more like an bus architecture or a hub architecture. It is going to connect all of these systems together, right? It is acting like a middleware.
Okay.
All right.
So, yeah. So thank you, Pradeep. Thank you for answering the questions. So before we sign off, I'd just like to thank everyone for taking out your time and attending our session. We shall be sending out the webinar recording to all the registrants soon. Thank you again for joining us today. Signing off on behalf of Team Spring People, and hope to see you again at our next expert webinar. Bye bye.
Thanks, everyone. Bye bye.